Good afternoon. Welcome to the tutorial on deep learning on mxnet. We have an exciting program here. So I'm Anima Anand Kumar. I'm a principal scientist. I'll be first covering the overview of what deep learning is and how mxnet has some unique capabilities that make it a framework of choice at AWS. And then we have Dennis, showing in detail notebooks on how to do deep learning in various different domains. And Sunil and Cyrus will take it from there and go deeper into the basics of what mxnet has in terms of ND arrays, as well as NLP models such as LSTMs. So, this is an exciting time for artificial intelligence and machine learning. We've had a lot of new results in pushing the boundaries in a variety of applications. And to me, what's been the driving force behind this are three aspects. In addition to the core deep learning algorithms, right, the equation that changed all this was the availability of data. So it was the creation of large-scale benchmark data sets, such as ImageNet and computer vision, that enabled us for the first time to see the power of deep learning. And the other aspect is also compute power. So without the modern technology, without GPUs, we wouldn't be able to run these large-scale training and inference tasks that are needed for deep learning. And so we should keep in mind that all these three should come together to make deep learning possible. And indeed, deep learning has now touched almost every area and domain. As I said, it started with the ability to do very strong computer vision, right? So to be able to categorize objects in images very accurately. And then we also now have very efficient speech recognition. So I think you're aware of Alexa from Amazon, as well as other products that use speech recognition for a variety of tasks. And processing natural language is in a way much more challenging because of the fact that language is a discrete quantity, right? Words are discrete or characters are discrete. And how do we process all the variations in language? And even there, deep learning has shown tremendous improvement in tasks such as machine translation. And the last one, I guess the most challenging one of them all, is when there's also autonomy, right, such as self-driving cars. And here you're using machine learning and fusing that with decision making. So all this has to come together, and you need to do reinforcement learning in the loop to be able to have efficient decision making in the end. And so deep learning, as you can see, has been trending over the last few years. This is when the first ImageNet contest results were announced, and then since then it's been on the upswing. Right, so as I said, one of the canonical tasks for deep learning has been object and scene recognition. So recognition is an AWS service that automatically gives you categories of various objects and concepts in an image, right? So for instance, if this is the sample image, you can see that there is a bay with 99% confidence, as well as a beach and so on. So this is the kind of output you would like from an image recognition service on what are the categories present, as well as what's the confidence level. So you could also be specific about certain types of images, such as faces, right? So you can have categories such as the emotion in a face, or whether there's sunglasses. So you can have these finer grained annotations for a subcategory of images, and for faces, recognizing faces as well as recognizing emotion and other qualities of a face will be useful. So you can also use deep learning for computer vision to do interesting things such as style transfer, right? So for instance, you want to transfer the style from the Van Gogh painting into this example photograph, right? So you can do that by combining the features from both these images. So the idea is you capture the statistics of the brushstrokes from the painting, and then you capture the object features from the photograph, and then combine them together in interesting ways to now create a new artistic image, right? So what is the concept behind this? So we have a convolutional neural network that has various layers of processing, right? So you feed in the input image, and then each layer here is a set of convolution operations, and then progressively you pool them and refine them and go through the different layers. And then at the end, there is typically a fully connected layer, meaning it takes in the processing from the previous layer, right, and does a matrix computation operation and some nonlinearity. And then in the end, you have this output, which is exactly the confidence level of what are the different categories present in the image. So in this example, you can say, for example, 85% confidence it's a dog. It's only a very small confidence that there is a cat, right? So there is this multi-level processing that is happening that makes it possible to capture different variations of objects in the image. And so why is convolution special? So convolution is special because you can have small filters go through an arbitrarily large image and capture the features in a translation invariant manner, right? So, and now if you have multiple layers of such feature processing, why is that useful, right? So the intuition is as you go deeper in the network, right, you get more complex, interesting features that capture real-world objects, right? So if you look at just the first layer, it captures basic shapes such as lines at different angles, right? But then if you go to higher layers, these simple features compose themselves into more interesting ones that will be efficient in recognizing real-world objects, right? So it's learning from the examples of images on how to compose the lower-level features into more interesting higher-level ones. And that's what you can see from this figure that's taken from the paper from Zieler et al., that as you go through higher layers, more interesting features such as, say, faces of this dog are activated well in a higher level filter rather than a lower level one. And so depth is also an important aspect for being able to get good performance, right? Because if you just look at the low-level filters, they capture very simple shapes, and you need the compositionality of going through multiple layers to capture more complex features that are closer to the real-world objects. And so that's why in computer vision, the best performance are obtained by deep convolutional networks. You need convolution to capture features in a shift invariant manner, meaning no matter where the object is in the image, you should be able to capture this. And you need the depth to capture more complex features, which a shallow network is not able to do. And we'll see later in the tutorial that you also need deep learning for sequence models, right? So if you think about a sentence, that's a sequence. In fact, it's a variable length sequence because the sentences can be of different lengths. And in this case, you need to keep a state or have some memory, right? Because like what you've said so far in the sentence is important for what you say next. And in fact, it can be bidirectional because you can like kind of look at context from both the sides and then make a prediction of what word you're going to be having in this part of the sentence. And so if you look at the forward model, right? So the way you can represent it is there's an input and output, but there is the state that feeds onto itself. And so you can unroll this and think of this as state propagating forward in time. An example of this, they're called recurrent neural networks because you have the state recurring over time. An example of this is, in this question and answering system, you can have an encoder state which encodes what the question is about, and then it feeds into a decoder that's, emits what the answer should be, right? So in this example here, the processing is done at the word level, meaning each word is processed into continuous state representation here. And in this forward model, each word is being fed forward on what state you should propagate next, right? And so once there is this encoding that is now fed to the decoder, right? So at each output of the decoder, you need to decide what you should emit for the answer. And at the same time, you should use that information to decide what should the next word be in the answer, right? So there are many possible architectures on how you should encode and decode in a sequence model, but the basic intuition is the notion of having memory, right? So memory from the past is important as you process the future, and you can have variable length, right? So there can be different lengths of sentences and different lengths of output, and you should be able to process that. So you could also do the same at the character level, and Cyrus will cover in more detail on how character level LSTMs work. But again, the intuition is the same, that you want to predict the next character, right? So you can start the sequence and be able to decide how you should predict the next character in your sequence. But these are examples of sequence models.
Sorry, can I ask a question? Can you just say what LSTM is?
So LSTM is long, short-term memory networks, but the details will be covered, so I'm just giving an overview here. Yeah. So I'll be giving now an overview of how mxnet is an efficient framework for deep learning in a number of these scenarios and the advantages that it offers. And then towards the end, I'll also cover the new AI services that Amazon AI has launched for image analysis, for having efficient chatbot interfaces, as well as having an efficient text-to-speech, which is Pollys. So if what I've shown here is one of the state-of-the-art architectures for computer vision. It's the Inception V3 network, right? So don't worry about the exact details of what each block does, right? But as you can see, these state-of-the-art networks are quite complicated, right? The architectures can now range to hundreds of layers. They can have complex interconnections, right? So if I ask you to implement this network from scratch, that's a non-starter, right? So we need efficient frameworks to be able to easily express such complex architectures and to quickly change and prototype and ask what is the best performing one for your current data set or for your current application. And so one aspect is how do we easily program and prototype these complex architectures. The other aspect is performance, right? So if you even send a single image through this network, it will require billions of operations. And that's why GPUs are the processing architectures of choice because these are highly parallelizable matrix computations, and GPUs offer much higher flops compared to a CPU, right? But how do we ensure that the program we write will exploit all this processing power and parallelize it to the maximum extent and have the code optimizations, right? So that's the second aspect. How do we have a package that does efficient computation? The third aspect is also memory management. As these networks grow bigger and bigger, how do we efficiently allocate memory as well as have the flexibility to deploy this on various platforms and frameworks that may have different memory capabilities, right? So can we easily trade off memory with computation and still enable running these very large networks? So, given that these are the criteria, right? So you can break them down into 3 parts. So you'd like a software package that has good programmability features, meaning it has efficient, rather primitives and simplifying network definitions, and a flexible programming environment that lets you, decide on how you want to, enable these networks. The second one, as I said, is portability. Ideally, you would like the same piece of code to be run on different platforms, different devices, right, and be able to have efficient use of memory enabled. And the third one is efficiency, right? So you'd like to have, as you increase your compute infrastructure, right, you could increase the number of GPUs, and ideally, you would like your throughput to correspondingly increase, right? If you double your number of GPUs, ideally, you'd like your throughput to double. And indeed, there will be some amount of overhead, but you'd like to minimize this overhead. And we'll see how mxnet is able to get state-of-the-art performance in terms of efficiency. So indeed, there are a number of choices for deep learning frameworks, right? So out of these, mxnet is the framework of choice at AWS. So the reason we are going with mxnet is mainly for 2 aspects. So one is that this is the most open source of all packages, and we have the Apache certification, and we have a very dynamic and active community. In fact, mxnet came out of university efforts, and there is a large open source community contributing to this. And the other is we are also developing it at AWS to have the highest efficiency, the best programmability, and portability for mxnet. So we'll make it easy for mxnet to be run on AWS very efficiently. So let us now dive deep and see how mxnet scores high on all these aspects. Right. So if you think about a choice of languages, right, there is a whole plethora of choices, and depending on your background, you may choose one or the other. Right. So for how many of you, Python is the language of choice? Yeah. Usually that's the majority. How about Scala? Yeah. I mean, in this venue, especially, Scala would also score high. R? Yeah. I mean, especially for statisticians, R is an important language, right? So Julia? Yeah. MATLAB? You probably don't want to admit that. So there is a whole choice of languages, right? But the performance varies if you just write them natively in these languages. But what mxnet does is there is an intermediate interface, right, based on a C++ code that will connect it to efficient backend operators. So it would be the CUDA deep learning library or the MKL library for CPUs that will operate in the back end. And so that's the idea that you're free to write it in the program of language of your choice and still get the same back-end performance. And so as you can see, this has the widest choice of programming languages. So the other aspect is the style of programming, right? So what I've shown here is a simple Python code, right? So Python is an interpreted language, right? This is the imperative style of programming where you just write the instructions line by line. Right? So this is easy to program, easy to debug. The programs are usually shorter. But of course, the downside is this is terrible for performance, right? So because you don't know what the next set of sequence of operations will be, you cannot optimize you cannot auto-parallelize, or you cannot allocate memory for efficiency. Right? So that's why when you want performance, you go with declarative style of programming. Right? So in declarative style, what you do is you first declare the variables, and then you specify the operations. So you have a compilation process where you'll get a computation graph. Right? And once you have this symbolic execution graph, you can do all kinds of optimizations. Right? So in this example here, we know that this intermediate operation would be overwritten in the next step, so you don't need a separate piece of memory to allocate these variables C and D, right? So you can overwrite that. So these kind of memory optimizations or auto-parallelism requires this computation graph, right? So without this, you wouldn't be able to do these optimizations because you don't know what the next instruction is going to be. And that's why, many packages such as TensorFlow and Caffe require a declarative style of programming. Of course, the downside is this puts more work on the programmer, right? So it's longer pieces of code. It's kind of more verbose. I mean, it could be harder to debug. And so this may not be always ideal. So what mxnet does is it lets you mix both of them. So meaning you can write parts of your program in the imperative style. So ND array is the multidimensional array that can be manipulated in an imperative style. And so in this example here, you can initialize these matrices, right? You can kind of do simple operations here. And then you can pass that on to your symbolic executor. So as you can see here, there are other parts of the code that will require loading in the network architecture and the various modules, right? There is the fully connected layer, there is the softmax output layer, and so on. So you can do these operations in the symbolic executor or the declarative style, but you can also import this variable C that was written in the imperative style. So you can mix these two flavors of programming as and when you require. So you can also do the opposite. You can embed your symbolic executions into your imperative style of programming. So in this example here, I'm updating the parameter through backpropagation, right? So there is the gradient that I'm computing, and then this the learning rate, and I'm updating this. But then to do this, I need to upload the network architecture. And you can write the network architecture in symbolic style and then bring it into your imperative style of programming here. So the intuition is the network architecture, right? So you can write it in the symbolic style because that's where a lot of optimization needs to go in, right? So there's a lot of room there to say, how should I efficiently allocate memory? How should I parallelize operations? On the other hand, doing backpropagation, right, will not require these optimizations. And that's why you can write this in the imperative style. So mxnet gives you this flexibility. So as a programmer, you can decide, for the parts that are very crucial for optimization, let me write it in declarative style. And for the parts that are less crucial and in fact are mathematically more involved, I can write it in imperative style and overall have a compact program. And so that was about programmability, that mxnet offers a whole choice of front-end languages for you to write your code, as well as mix imperative and declarative style of programming. So let us now see how mxnet is also easily portable. So mxnet supports amalgamation, which means that you can fit all your core library and dependencies into a single C++ file. So you can easily compile it on different platforms. I'm not sure.
Orange, banana.
So in this example here, this was run on JavaScript, and you can easily get now a smartphone to detect objects, right? So detect day-to-day objects. So this procedure makes it easy for you to easily deploy this across different devices and platforms. So also when you're deploying mxnet on devices where memory is a constraint, or even on our usual GPUs, right? As these models get bigger and bigger, memory will become a constraint. And so the question is, can we also think about optimizing for memory? So in the example here, right, what I've shown is the usual forward and backward pass when you're doing training of a deep network. So meaning you start, this is the input layer, and during the forward pass, what you're doing is you're computing the activations at every layer, right? So this is typically a set of matrix operations, and then you're doing a nonlinearity. And so depending on whether it's convolution and pooling for computer vision, or in a fully connected network, it's just matrix multiplication and nonlinearity. So those would be the set of operations here in the forward pass, right? So multiple layers, you do this. And then in the backward pass, what you're doing is you're updating the weights, right? That's the stochastic gradient descent step. And so for that, the chain rule says that you will need to use information about what the activation is at that layer, and then do the weight update and pass it forward, right? So this is the backward pass. So each iteration of deep learning training will involve this forward pass and backward pass. So if you were to implement this computation graph as it is, right, you would need to store all of the activations in memory, right? Because you have to first wait for your forward pass to finish, and then update the weight through the backward pass. And this is very expensive, especially if you recall the example I showed in the beginning that had hundreds of layers, right? So your memory requirement is growing linearly as you keep increasing these layers. And so to store all that, when that's not feasible to store it in memory, we can now do something else. So what we can do is we don't store everything in memory. We only store parts of them in memory. So we can divide up the layers into segments and say store only this head node in memory. So what we'll do for the other, right, we still need information about these activations when we are doing the backward pass. But what we'll do is to compute that on the fly, right? So when I'm doing the backward update, I will recompute it rather than just take it from memory. And what you need to do is to recompute this, you just need to start from here, because you already have stored this, so you invoke this and then use that to recompute the activation here. And then you use that in your backward pass update. And so that's the idea that with this segmenting and storing only parts of your layers in memory, you can do trade-off between how much memory you require and how much extra computation you need to do. Right? And with this, you can reduce the memory requirement to as little as square root of the number of layers. Right? So the earlier one, just the plain implementation of the computation graph would require linear requirement in memory. But now you can just reduce it to about order square root in the memory cost. And so this is the paper by Tianqi Chen and others that has the details of how to do memory optimizations. So in mxnet, this is very easy to do, and this is already implemented. And to give you some idea of numbers of how much you can reduce, right? So the ResNet is, as I said, one of the state-of-the-art networks with hundreds of layers. And you can now see a huge reduction in memory requirement. And same for the LSTMs, right? They're also very memory intensive, and you can reduce this. So the key here is we are not doing any compression or any lossy operation, right? So you're still going to get exactly the same answer as you would in the naive setting. But by doing this trade-off of which ones you store and which ones you recompute, you're able to drastically reduce the memory requirement. And so that's a capability that mxnet offers. Right, so I talked about how mxnet is easily portable. There is amalgamation, and you can easily deploy it in multiple platforms, as well as have the flexibility to do trade-off between memory and computation on a range of different devices. So now let's see how performance is also an important win for mxnet. So indeed, if you were to write parallel programs from scratch, right, that's not an option for deep learning. Right? So classically, we had MPI, and we would look into each operation and ask, how do we coordinate between the different machines? What should be sent over, right? How, when should these communications happen? But this is clearly not scalable for a deep network that has just, as we said, billions of operations. Right? So even with just 2 GPUs and a CPU, what I've shown here is the example of the forward and the backward pass. Right? So each GPU has its own network model here. So it's taking in its share of data. Right? So there is this overall data in the CPU that gets sent over one part to the one GPU and the other part to the other GPU. And then locally, they do the update, right? So they're doing a forward pass in the network. But then you need to communicate to the CPU to update the weights, right? So you send over the gradients get aggregated in the CPU, and then you have to update this. And you can see there are already just so many different connections, right? So don't worry about the details. The message here is that this is just too complex to be done manually or to be done at low level. So how mxnet gets around this part is to have a parameter server architecture where the various workers in each round will share their gradient updates with a central server, and the server will aggregate them and push it back to the workers, right? And this is done iteratively at the end of every batch. And so the thing that makes it efficient is that the aggregation is done at a local GPU itself rather than at the CPU level, right? Because the lowest level workers are GPUs, meaning you send part of your data to each of the GPU, and then they do a local update and get a gradient information. And so here, one of the GPUs itself acts as a level 1 server, meaning it takes the information about the gradients and aggregates and sends it back. And this is done now at a much faster speed than it would take to go to the CPU, right? So, and that's what makes it a lot more efficient. And indeed, when you communicate to the CPU, you're just doing this, the communication is only this aggregated information and not all the updates from each of the GPUs. And so that's what this hierarchical parameter server lets you do. It lets you aggregate locally at the GPU level and then send in only the aggregated information back up to the CPU. Right. And so when we talk about scaling, you can think of it at various different levels. So one is scaling within a GPU, right? So indeed, GPU has thousands of cores, and how to do parallel operations within that is optimized by the CUDA libraries, right? So this is why GPUs are much better than CPUs for most of these matrix operations. But then we also now need to worry about scaling across multiple GPUs. So if you take a P2 instance, that's a GPU instance, and the 16x large means it's a 16 GPU instance, right? There's 16 GPUs on the same board. And so how does mxnet scale in this setting, right? So that's the first plot I'll show. And then the second one is sometimes you may need many more GPUs than just 16, right? So this is where you can now get multiple such P2 16x large instances, combine them together and get a larger instance or a larger node. So we'll see the scaling in each one. So all these benchmarks are available on GitHub, and you're welcome to run through them. And so I guess the slides will be made available, so you can, yeah. So what we see is on the 16x large instance, we get up to 91% efficiency for state-of-the-art networks such as the ResNet and the Inception v3. Right? So what I've shown here is I'm doubling the number of GPUs. Right? I'm going from 1 GPU to 2 and 4 and so on. So the ideal plot is you expect the throughput to double. Right? So this is the number of images processed per second. And then, but what happens is you're slightly down that curve, but not by much. So 91% is a very high number for efficiency, right? So you're getting a lot out of expanding your GPU instance here. So now we can ask the same question for a much larger setting. So where we take 16 such instances and put them together, and that's 256 GPUs. And there is indeed a drop in efficiency, but it's not much. So now we have 88% efficiency. Right? So, I mean, the details are on the GitHub website, but this was run using the CloudFormation templates with the deep learning army, and we'll see more details of how to actually get this going. And so this is all was on the ImageNet images. And in a separate experiment, if we if you wanted to tune a ResNet from scratch and get state-of-the-art results, right? So that's also available. The benchmarks are available because this number is just the throughput and not the full training process. So, but the message is you get a very high level of efficiency using mxnet. So if you're running deep learning in production, or you really have a very large-scale model that requires a large number of GPUs, right? That's when this becomes very important to have an efficient deep learning package. And mxnet scores very high on that. So indeed, we have a number of exciting things under development in mxnet. We have extensively done a documentation overhaul, and you can now see a documentation in a variety of these languages that I described earlier. And we'll also be adding more capabilities and operators for doing a rich set of operations in linear algebra, including sparse data types. The traditional deep learning does not require sparsity, but if you think about other machine learning frameworks, right, sparsity will be important. And my area of research has been to ask how we can enable tensors in deep learning and how tensors offer much better expressive power compared to matrices. And we are enabling a lot of that in mxnet as well. So I'll just show you briefly like how tensors can go beyond matrices and provide rich expressivity, right? So the idea is, if you think about your data types, right, in general, they are multidimensional. So if you think of an image, it is usually width, height, and the number of channels. In a standard image, that is RGB, but it could also be hyperspectral with more channels. Right, so in general, what you're having as an input is not a matrix, but sometimes a higher dimensional one, right? And even if your input is not a tensor, definitely as you go through layers in your network, you can have more multidimensional objects. And so the one question is, can we have operations that exploit this multidimensional nature? Right, so to give you an example here, this is the classical AlexNet network for image classification. Right, so this is the input image, right? So you have the width, height, and the RGB, and as it goes through the different layers, right, the number of channels varies because it depends on how many filters you applied to your image. Right, so these are the various operations. Don't worry about the details, but what you can see here is these are all really three-dimensional objects, right? But then finally, when we want to make the decision about what are the categories present in this image, we flatten them. Rather, we convert them into matrices and do the operation, right? So this structure is lost as we go through the fully connected layers. And so, that is the usual setting, right? You flatten and you do fully connected layer. But what we instead proposed was to ask, can you do tensor operations and come up with more compact and better networks that can learn better? And so the intuition is, if you can have a tensor contraction layer where your input is a tensor and your output is also a tensor, but most likely of a lower dimension, right? So you're doing dimensionality reduction, but with these multidimensional objects. So I won't go into details, but this has been implemented in mxnet, and you can have this layer, right? So just to give some preliminary results, what this will result in is a much more compact network, in fact, with a better accuracy. So the baseline, this is the standard network where there is the fully connected layers with matrix operations. But if you replace them with a tensor layer, you get a huge amount of space saving, in fact, about like 44% space saving and even a better accuracy. And so the idea is there is a lot of opportunity to design architectures that exploit multidimensional nature of the objects we are processing through different layers of the network. And these are now also enabled in mxnet. So in the last part, I want to give some overview of the other AI services that we have recently launched. In the beginning, I talked about recognition as a managed service for large-scale image recognition in real time. I'll now talk about Lex, which essentially is Alexa in a box, right? So I mean, if you remove A on either side, you get Lex, right? So that's the idea, that Lex helps you build chatbots very quickly and harness the power of Alexa. So the idea is this is really the future of how we interact with machines, right? So if you think about the very first generation, it was really machine-oriented interactions, right? So it was this laborious task of, okay, how do I write it in assembly-level language or very low-level language to be able to get machines to do what I'd like them to do. And the second generation got better, right? That's our current generation in a way, where there are higher-level programming languages and abstractions that make it easy for us to tell the computer what to do. right? But really the future is where the machines understand what we want and do it more automatically and seamlessly, right? Rather than having to have a detailed set of instructions. And that's where Lex is a step in that direction because it helps developers easily specify what kind of chatbots they'd like to build and how that should be interacting with the customers. Right, so it's powered by Alexa, meaning you can harness the knowledge graph of Alexa through Lex, and it has a number of enterprise connectors and interaction through also text messaging, such as the Facebook Messenger and Slack. So to give you an example of a chatbot interaction, right? So this is a standard one about flight booking, right? So if a customer says that, oh, book a flight to London, we are here in London, so there are different parts to this interaction, right? First, the machine has to do speech recognition, so it has to parse what the individual words meant, and then it's the natural language understanding part. So it should figure out that London means usually London Heathrow, right? So that's at least the default. And flight means flight booking, right? And so this is where the knowledge graph will be useful because this knowledge is already built into the system of what the words mean in terms of the actual knowledge structure. And so you can fill in the table where there are already defaults or the information is gleaned from ASR on for instance, the origin is a default, the destination is now given by the customer, but then you have some missing information. And so now if a decision can be made on what else to ask the user, get this additional information and keep the loop going, right? So what Lex does is it helps developers easily and quickly build these chatbots to interact with the customers. And so the other service that I want to talk about is Pollys, which automatically converts your input text into speech. So it's a fully managed service, right? It has a variety of choices. So it has 24 languages, so it's a lot language coverage, lots of different voices as well, and it's low latency, so you can do real time. So let's quickly hear some samples on what Pollys can do.
Alice was beginning to get very tired of sitting by her sister on the bank, and of having nothing to do. Once or twice she had peeped into the book her sister was reading, but it had no pictures or conversations in it. And what is the use of a book, thought Alice, without pictures or conversations?
Yeah, so this way you can now easily, generate, voice-enabled information, right? So you can take any piece of text and quickly generate these recordings. And so the idea is Pollys has a number of capabilities. It can, automatically recognize a number of things, right? Like for instance, what does F here stand for? Or how should I customize the pronunciation depending on the context?
Today in Seattle, Washington, it's 11 degrees Fahrenheit.
Right, so F is Fahrenheit, so that it recognizes.
We live for the music live from the Madison Square Garden.
Right, so English is a complex language, right? So the pronunciation changes depending on the context and whether it's a verb or a noun. So, so these are already built into. So Pollys tries to disambiguate whenever it can.
How much wood would a woodchuck chuck if a woodchuck could chuck wood?
Right, so I wouldn't even try to say that. And so, and also sometimes you can specify, right? So the user has the control to specify on how to add more, kind of say that this is a phone number. And so Pollys can adapt its pronunciation depending on this information.
Richard's number is 2,122,341,237.
So you wouldn't want that, right? But I mean, here it's not clear it's a phone number. It doesn't say phone number. Who knows? It could be his, salary, right? Probably not. But So that's the thing that but if you specify that this is a phone number, then Polly can get this in a semantically meaningful manner.
Richard's number is 212-234-1237.
Right, so it adjusts to that. And of course, there would always be settings where you're not happy with the pronunciation and you'd like to customize, especially with names, right? So I know my own name is quite tricky to pronounce at times. So you can do that with Polly.
My daughter's name is Kaja.
Right.
My daughter's name is Kaya.
Right, so you can customize whenever required. And so that's the idea that Polly is a managed service that allows you to process large amounts of text and get real-time voice output, and also has the ability for you to customize as required. And so at AWS, we are also committed to having a number of community engagements with developers, with academia, with startups, and we have a number of programs for cloud credits. So if you're interested in that, you can talk to one of us. You can also go to the website. There's also credits for education. So if you're teaching a class, we can enable that as well. So if you're interested in that, come talk to us after this. So I'll stop here, and then Dennis will take over. Thank you.
Okay. Well, let's begin. Hopefully I won't diverge too much from the podium, so you can all hear me. So I'm Dennis. I work for AWS as a solutions architect. I'm based physically in Luxembourg, but I cover EMEA in terms of machine learning and AI type engagements. I have a PhD in machine learning, focusing more on the reinforcement learning side, in case you're wondering. And then if you want to get in touch with me, Twitter is probably one way to follow and then send a message, so take a note of that. Cool, so let's begin. I think Anima already did a great presentation as to mxnet, various features that it has. And so for the tutorial, for this section, what we're going to do is try to launch a deep learning AMI, Amazon Machine Image, with all the different deep learning software, which is mentioned here, installed. And then we're going to launch a Jupyter notebook and try various experiments, various networks, and different tutorials there. So in this process, it's extremely important that all of you guys are successful in launching the Amazon Machine Image and then launching Jupyter, so you could follow through all the steps. Now, mind you, you could obviously still learn by observing what's shown on the screen, but yet I think it would be much more interesting, interactive if you manage to follow through with your own computer. So that's what we need to do. And of course, launching the Amazon Machine Image AMI, the deep learning AMI, you can do it on graphical processors. And so you could launch it on a P2 instance, which is one of the newer graphical GPU instances on Amazon. But you can also use the older, cheaper G2 2x large instance, and we'll talk through that as well. So let's kind of begin with actually getting everything in place. Yes?
Which region is this?
Basically, the deep learning AMI would be available in North Virginia, and I think in Ireland as well. But I think, up to you. I've launched my AMI in Virginia. But again, whatever works for you guys. So step number one, follow this link. It's dl-ami. on Bitly, and this will lead you to an HTML file with detailed instructions of all the steps you need to follow to launch the deep learning AMI. I'll do this in front of you as well, kind of show you the steps, but this web page will be helpful to kind of look back and refer to the material when necessary. Yes, and exactly. So we have Cyrus, we have Sunil, and we have Joe. They're all here available to kind of help you get going. Don't hesitate if you have any questions, any problems, even if this looks silly, ask, because again, we want you to get that going on your computers and not be blocked, because otherwise it might not be as hands-on for you to follow the tutorial. Okay, so I'll refer to this screen later on. Did you manage to open the instructions on that link, the dl.ami? Anybody is still catching on? No. Okay, good. So let me switch to a browser here and try to kind of replicate these instructions, perhaps. Okay, see that? So, if I go to Amazon Web Services console, make that larger. So on EC2, I can launch a new instance. Now I've got my instance running and configured already, so if we go here, you will see an mxnet tutorial running. The region, as you can see, is North Virginia for me. But to launch a new one, you'll just click Launch Instance. And by the way, maybe I should ask first, do all of you have your AWS accounts in place? Not everybody. We do have credits available for you guys, so if you'd like to kind of sign up, there's a $25 kind of credit that should cover the cost of running the machines and so on. Link to sign up. Yes, so that's the one. No. No, this is your instructions. Oh, okay. Oh, there they are. Yeah, yours is deep AMI, mine is DL AMI, but basically these are instructions to follow. Okay, so I don't want to go too fast here, but how many of you are not able to log into an AWS console and launch an instance? Okay, so maybe 3-4 people. Please ask our lovely colleagues. Okay, so once you're in the console, you want to launch an instance. I mean, this is the key thing. You want to get a GPU-based instance running with a notebook there. And we want to search for a particular Amazon machine image. So you need to switch to an AWS marketplace and search for deep learning. oops, deep learning AMI. And you have two versions that will jump at you. One of them is a Linux version, Amazon Linux, and the other one is Ubuntu. So depending on which you are more comfortable with, launch the one. I think in the instructions that you've got on that web page, it actually points to the Amazon Linux version. But again, I hear Ubuntu is really popular, so don't hesitate to jump there as well. And once we select one of these two, Deep Learning AMI Ubuntu version, let's say, you then need to pick a machine, a type of machine. Now, of course, these are the instance types, families and names, and the ones that would work, or probably are most recommended, are GPU-based instances. So I was talking about G2 2x large, for example. This is the smallest kind of regular workhorse GPU instance that we've had for a while. And then you also have the P2x large, P2 8x large. If you really want to go big on GPUs, that's probably your choice. But really, for this tutorial, you could just go with G2 2x large. I mean, you can even go with a non-GPU instance, but some of the training steps will take longer. And so I think at the minimum you should go with G2 2x large. That would be recommended. So that's what I'll select. After I select the type of instance, I can basically keep the other details. Well, depending on your account setup, you may have a VPC. So this one says launch into EC2 Classic, but you can also pick a particular VPC, virtual private cloud, that you want to launch into. You may not even have an EC2 Classic option depending on when you set up the account and in what region. So let's say I'll go with my default VPC. Any subnet will do. So really the only thing you want to ensure in this screen is that you have a public IP address that that machine will get, right? And so make sure that auto-assign public IP address is actually selected as enabled. Yeah?
Anybody hasn't had any problem launching an instance because you're not permitted to?
Yeah.
So because there's something happening here, I wanted to.
Although I have the credit, but
You'll have the credit, but it doesn't let you because that's the kind of instance you're not permitted to. They get a stranger. You have basically no right to launch that kind of instance, and then they have to open a ticket with support in order to give them permission. And it's not a matter of credit or money.
So are you talking about G2 2x large or P2? P2, but pick G2.
Pick a G2, that one's
Yeah.
right.
Like I said, guys, you can even go with a non-GPU instance, but I would, like I said, I would recommend G2 2x large. It may be a limits issue where when you start using a particular type of instance, each instance has its own soft limit set up initially, and you may not be allowed to use it until you explicitly request it because it's a highly powerful specialized machine. We want to make sure there's a reason for launching it. G2 works?
do we need to add storage or we just get the launch?
So let me go there. So once you make sure to enable the public IP address, you can just, you go to add storage, but whatever is selected should be enough, right? So the default configuration is fine. Again, as you're going, just remember, public IP address, type of instance choice, public IP address, and then tags. I usually recommend adding a tag just so you know what kind of machine that was for you later on to clean up, right? So I would at least add, name and then mxnet tutorial or something like this, right? Just to remind you why you've launched this machine, or delete me later, or whatever you prefer, right?
With a G also, I'm not able to
G2
do it.
2x large, you're not?
Yeah.
So what does it say?
I have a limit of 0.
For G2 2x large.
So try a normal C4, you say? Try a C4, try a normal CPU instance. All you need to do is to make sure the context becomes CPU and not GPU when you're running code. Just open normal.
How long have you had your account?
Well, it was since 2012, but it
Okay,
got
so
deactivated.
it hasn't been activated, or?
It got deactivated, and I just got it deactivated.
I see. So I know that there are sometimes limitations like this one. The system still feels that the account is not fully activated for whatever reason, and that could be the issue. Like, see if you can launch any of the instances, right? Like C2, C4, M3, whatever type.
Yeah, Yami has MKL.
Hmm?
The Yami has MKL, so it's pretty fast.
Right. Okay.
Okay, C4 worked here, so you should work. Elsewhere, this is a new account, right?
Yeah. Yeah, but it's well, not only, like, there's a lot of it. Yeah, it's not the first time.
And it usually works to your benefit because you don't end up with a bill at the end of the month without knowing it.
Okay. How many of you are here or are managing to launch the machine? Or all right, some number. Okay, great. So the key next step is to make sure you have the right security group, because we need to set up an SSH tunnel and SSH into the machine. If you haven't gotten a security group created previously that has SSH port open, I usually have one that's just SSH only, right? That's the only one. So I would choose an existing security group, such as this one, SSH open, right? That's something I've created previously. All you need is to have port 22 from any kind of outside source. But you can create a brand new group and basically all the settings are already given to you, and that may be the safest to choose. There is already some auto-generated name for this group. Again, you can clean up later on.
Is it enough to use our old IP except timing instead of the...
You mean instead of opening it to the whole world? Theoretically, it should be good enough. But again, depending on how the networking set up here, one never knows.
Theoretically, you probably want to go to a VPN of your company. From there, you want to go out. But forget about that here, because there's a number of ports that are open here. We had to actually request the port to be open so you can access your notebooks from here. So please stick with the ports that you see here.
Okay. So, no?
Did you want an 888? Or 8 in order to be able to?
No, because we're doing SSH tunnel. Yeah. So once you've made all these choices, effectively the last step is specifying the key, right, with which you're going to SSH and log in into the machine. Again, if you have a key available, accessible on your laptop, great. You could use that. I'll show you. So if I click launch, it tells me to choose a key pair. I can create a new key pair where you need to download the private key, and your PEM file. I have my main key that I use, so I just choose that. But again, you need to have access to that key from your laptop. So if you haven't created a key before or saved it on your machine, make sure you have a key created. And then we should be off to the races.
The key goes into region, right?
Yes.
So the key you're using, if you're using a region that you're not usually used to, you have to upload the key, otherwise you have to relaunch the machine.
Right, right. But again, if you're in a new region, just create a new key. It's simple enough. It'll be a throwaway key, and you can delete it later on. Okay, so it looks like my machine is running. The next step for me is to create an SSH tunnel. Now, why are we doing this? We're going to launch a Jupyter notebook on that instance, right? And Jupyter notebook creates a web server, and you need to be able to access that web server from your notebook. Sorry, from your laptop. That's confused terminology here. So from your laptop, you're going to be connecting to the web server, but we don't want that web server to be world reachable, right? Anybody could just come in and start experimenting on your instance and running Jupyter notebooks. So from the security point of view, it's best to simply create an SSH tunnel from your laptop to that web server. The Jupyter notebook is running on port 8888 by default. You can override it, but that's what it's going to do. And then we're going to create an SSH tunnel from our laptop to that web server, so that then you can use your localhost IP or localhost domain name. However, Cyrus mentioned earlier that we had to ask permission for networking guys to open a port for us, and it's not port 8888, it's actually port 8889. So on your local machines, you will be connecting to the notebook at port 8889. However, on the instance that's running in AWS, it's going to be the standard port 8888. So this is what I'm going to do. So I need to essentially copy my public IP address to which I'm going to be connecting, establishing the SSH channel, SSH tunnel. And here's the command for doing this. Again, if you guys are on Windows, then the instruction file that I've shared earlier has Windows instructions on using PuTTY and how to create a tunnel using PuTTY. But the key thing is that on your own laptop, the local host, the port should be 8889, just like I was saying, whereas on the remote machine in the cloud, the port is going to be 8888. And then, so on Unix or on a Mac, you simply say -L. You can add more flags here to kind of not output anything from that tunnel. But I find it convenient to just say -L. I need to supply my key that I've created or used. In my case, it's main.pem. So -i with a key. And then if you're running Ubuntu, the username is Ubuntu and here's where the public IP goes. If it's Amazon Linux, the user is ec2-user. And so let me try doing this here, all right? SSH-L, localhost 8889, localhost 8888. My key is actually stored in a folder, and then Ubuntu at the IP address. So I have a previous tunnel running. I may need to stop that. Actually, maybe what I need to do is let's see. How are we doing for time and breaks? Are we past?
12 minutes.
12 minutes, still a break?
12, not break, yeah.
Okay, perfect.
Probably good time.
Yeah. Let's see what's going on here. So I think my previous tunnel has not stopped yet. Okay. Oops. Okay, there it is. So I've logged in into Ubuntu, and at the same time I've created a tunnel. So port 888 on that remote machine is now available as port 8889 on your local host. There are other things that you typically want to do. I usually run screen to make sure that my sessions are not interrupted and I can return to a session. So something like screen-as mxnet. In case my SSH is disconnected. And then additional steps are kind of listed in here, right? You want to run a git clone command to get the mxnet notebooks. These are the tutorial notebooks that we're going to go through together. So that's a simple command to execute. And then once this is done, you can basically, well, you can cd into a particular directory and then start Jupyter. So let me try to do that. Okay. So I have my outline IPython notebook, and that's basically is the one that contains the root links to all the different tutorials. And so at this point I can just run Jupyter. Notebook, and technically it should be sufficient. I could say no browser, because usually Jupyter tries to open a browser on the machine on which you're running, so it can open that page automatically. Let's see if this works. Okay. So Jupyter is running, and the last step in this kind of handshake of a security procedure is to make sure to use this URL that Jupyter shows to you, because it contains a login token that you need to supply for it to recognize you as a valid user. It's the basic authentication mechanism. There is a way to disable authentication just so that you can open a port 80 and go there and look at your Jupyter notebook, but that's not secure. Anybody in the world can then connect, and we don't want that to happen. So we're trying to show you the best practices in doing this. So I will just copy this token, or this URL, go to my browser. Oops. Paste that. It's hard to see, but basically it's just connecting to localhost. However, the one thing you need to know is that URL contained port 8888, which is what it is on the remote machine. But you recall that on our local machine it changed to 8889, so we need to change the 8 to 9 in that URL, and oops, that's not working. Okay, let's see. Maybe there were some issues with the tunnel when I was setting it up. Let me try to do this again quickly. Detach the screen, exit, and let's see if the tunnel is starting. Should be working, but let's see. Screen -R. Let's try that again. Okay. I don't know, maybe something was a hiccup with the tunnel because I had the previous tunnel running. But anyways, this is the step that we want you to get to. And that's the start of all the notebook tutorials that we're going to go through. You want to click on Outline IPython notebook, whatever. And we've got some links to the tutorial notebooks that we'll be kind of going through after the break. We'll start with some basic concepts, and then we'll jump into mxnet, and then my colleagues will continue with other cool things. So let's make sure you're all able to get there. If there are any questions, please don't hesitate to ask. We want you to be there. Anybody still struggling? I don't see too many smiles. In fact, I will use a different machine. This instance I launched just for demonstration purposes. I have slight modifications to the notebooks, and I'll set up a different tunnel meanwhile. Yeah. Just run that exact command. In your instruction file, that long web page, the git clone command is at the very, very bottom of the page, at the very end. On which account, sorry? No, I'm not sure actually, yeah. No, that's it. So if you've gotten to the Jupyter page, this outline, you're good. I think we'll have a break, and we'll start with...
Now I see mxnet. That's it, right?
Yeah, probably. So we have a break. It's a half-an-hour break. Feel free to make less of a break and stay here if you still need to set up your machine. And we'll restart with our tutorial in exactly, well, less than 30 minutes now. Yeah.